Thank you. So this is, I think, the second seminar I ever give. So thank you for having me here. It's very special to see Lisbon and everything. So I will tell you about some of my work on ringdown modeling. It's work I did as a PhD and some work I'm continuing doing as a postdoc. And then these things.
No.
Okay, I'll just click. So I will begin with introducing some of the ringdown, which I think all of you probably have already seen at some point, but I'll just do a very quick introduction, and then I will motivate why we care about ringdown, or some of us care about ringdown, and then I will introduce you to some packages that we've been working on getting out. So the qnmfits package and the ringdown package, as well as a step-by-step of how we built these packages. And then I will move on to how we built upon that itself to do a surrogate model just for ringdown. And then some more recent work that I've started doing away from the typical ringdown waveform stuff. So as you all know, we have 3 stages to binary black hole systems. And so I will be focusing only on the very last part. Of course, there's no defined time as where ringdown starts or where merger ends. So we will just kind of keep this window a little bit wide to do these studies for now. So quasinormal modes have their characteristic frequencies, which are determined by the final mass and the final spin of a black hole. And so they are denoted by the LMN indices, where N is a fundamental mode, and then anything that is N1 or above is called an overtone. In the ringdown area, there seems to be a lot of different notation and conventions, so this is why I'm defining this. The word overtone for N is not always good, especially because N equals 0 technically is also an overtone, but it's a fundamental. And so perturbations theory is what gives us this set of quasinormal mode frequencies. And so we define mathematically our analytical ringdown equation in the following way. It's composed of 3 different parts. So you have your quasinormal mode amplitude. So this is the script A. And for each quasinormal mode frequency, omega, given by the equations, it has its corresponding amplitude, also denoted by LMN. You will see a plus sign, plus and minus sign on top of the A and script A and the omega. And that just means that there are 2 solutions. So each quasinormal mode has 2 co-rotating and counter-rotating solutions with a black hole. So we denote the co-rotating as plus and the counter-rotating typically as minus. And so when you solve this using Topolsky's equation, you get the solutions in terms of spin-weighted spheroidal harmonics, because we're talking about Kerr black holes, so they are axis symmetric. But because we are working with numerical relativity waveforms, we want to change our basis to go to the spherical harmonics instead of the spheroidal harmonics. And in order to do this, we have this CLL prime M, which is called this spherical spheroidal mixing coefficient. And so that is a trade-off from going to one set of functions to another. And so in the end, our analytical model looks like this. And it's, well, I should say it's quite easy at this point, because you know your spherical harmonics, and then you already can solve for these spheroidal functions by solving Topolsky's equation, as well as the quasinormal mode amplitudes. And the only thing you're left with is really your quasinormal mode amplitudes. And so that is something that then you need numerical relativity to fit for, because there's no closed form solution that you can just solve and say, this is my amplitude for the specific mode. So you need to fit for those with some sort of waveform. And so part of the motivation for doing this is that there has been a lot of exploration in the ringdown area. A lot of things have started exploding like since 2014, and you can say before, but it became more and more unpopular. So people started looking at higher order modes, because typically when you look at a gravitational waveform, in the past people looked at the L equals N equals 2 mode, which is a dominant gravitational wave radiation mode. So a lot of the models were built with just that mode, or the 2 minus 2, but then people started adding more and more modes to try to really be able to model more of the power coming from different binary black hole systems. Additional work has come out looking at retrograde modes. So these are the negative, the counter-rotating solutions to a binary black hole. You also have the overtones that I mentioned. So as you add more and more overtones, you're really just, in a way, adding more corrections or getting closer to the correct solution. But the problem is there is an infinite number of modes and overtones. So at some point you start overfitting and you cannot you cannot get any better, because there's numerical relativity error that you have, and then there's computational constraint that you also have. And there's also more recently work looking into the quadratic modes. So these are modes, for example, you have the 2-2 mode that uses itself as a source. So you have the 2-2 cross 2-2 mode that then becomes equivalent sort of to the 4-4 mode. So then you have all these higher order terms that people are starting to look into and try to model more. And then you have, of course, this no hair test, where you're trying to figure out deviations from GR, looking at these modes. So you add a little bit of a deviation. So you take your quasinormal mode frequency, omega, and then you add a small term. You can do that with the amplitudes as well, and try to see how well you can constrain things with observation, for example. And furthermore, in the past 4 years or so, there has been work on including memory waveforms. So memory is an effect that has been typically ignored. Numerical relativity simulations for SXS, Maya, and RIT are usually extracting these waveforms, what we call in an extrapolated way, where you're essentially solving Einstein's equations at specific radii and extrapolating to future null infinity or to the observers. And the problem with this is that when you do that, you're not really solving Einstein's equations at all points. So you're missing out on this memory effect that arises from solving it fully. And so when you use something called Cauchy characteristic extraction, which I will go back into that in a little bit, you're able to really capture all this memory dynamics. And so one of the reasons why this also becomes important is because it kind of seems to, it's related to changing the frame at which you're looking at your waveform. And that will become clearer. I have some plots that I can show on that too. And so there have been some recent models, I think within this year, or at least the past 6 months, that have come out with adding the 2-0 memory modes. So modes with m equals 0 tend to have the highest memory. And so people are starting to add corrections to make their waveforms more and more accurate. And so maybe the most obvious reason why we care about ringdown is because it allows us to be able to test GR in a very easy way, in the sense that we can use perturbation theory and we have clear analytical solutions. And then we can compare what we get from ringdown to in spiral and see if we are able to independently come out with the same parameters, for example. And with the higher next generation detectors, we'll be able to test this ringdown a lot better. Hopefully, we'll see how well we can do, but I have high expectations. And of course, we need to be ready for that, because where we are now, we are pretty far from being able to be able to do proper parameter estimation. So we still have some time anyways to develop better models. And so the first thing I will talk about is I will kind of try to sell you a product now. So we have two codes. One is called qnmfits and the other one is called ringdown. They're almost exactly the same thing. What they're doing for is they're solving for your quasinormal mode amplitudes and also the remnant mass and the remnant spin. So what you can do is you can take any waveform you want. You can give me a time array and an array of modes, or you can give me an SXS waveform, maybe in the super-res frame, or an RIT waveform, and put it into this machinery, and you're able to extract the quasinormal mode amplitudes, the remnant mass, and the remnant spin very accurately. So depending on if you prefer to use Python or Mathematica, that's where the difference between these two packages go. They have the same way of solving these. They use linear least squares method to solve for these amplitudes. However, the Mathematica package does have this limited eigenvalue mode method of extracting the amplitudes, which is essentially almost exactly the same as linear least squares. And the results have been compared, and they're within machine error. They can all do multiple modes, so you don't need to restrict yourself to a few modes. You can do like all the overtones you want, all the retrograde modes you want. The only thing we haven't implemented yet is the quadratic modes, but I think that's underway at the moment, or at least that's something we talked about doing this year. And the qnmfits has something that we call a greedy algorithm, which I will explain to you in a little bit, while the ringdown doesn't. So this essentially has to do with if you want to build a waveform model, or if you want to extract amplitudes for a specific binary black hole system, which modes do you pick? You can manually pick the modes yourself that you're interested in, but we are trying to have some alternative way to motivate this, and that's what the greedy algorithm does. And they both just minimize the residual, the power residual between these modes. And I will explain all of these points much clearer, but this is just to give you an overview of what this will look like. Yeah.
I already have a question. So does it also give you the quasinormal mode frequencies?
Doesn't what, sir?
The quasinormal mode frequencies?
So we get the quasinormal mode frequencies from the package called QNM.
Okay.
And using that, you can then try to build your model in a way that then you can extract the quasinormal mode amplitudes.
Okay.
So we use QNM to get the omegas, and then at that point we have everything from here onwards, but we are still left with this as a big question. And in order to do this, then we have to use some video package or algorithm.
Okay, but the frequencies you also wouldn't know in advance.
If you specify, well, if you give it a waveform, you already know the final mass and spin from numerical relativity. So you can fit it that way.
Okay.
But you can also do it.
The gives you already.
Sorry, it does two. Okay, so the fit does two things. We have two fits technically. One that just looks at the amplitude given the final spin and mass, and one that estimates it.
Oh. And
the errors, I will show the errors as well. But yeah, it just uses also interpolation essentially, or it uses Milder-Meads method to try to get this final mass and spin. Yeah.
Okay. And where do we find this code?
On GitHub. On the website there. I had some QR codes, but then they expired. Yeah, so the qnmfits is part of the SXS collaboration because that's the one. I should also mention I helped develop that with Elliot Finch, who was a Greg Cook student and is now at Caltech as a postdoc. And the second one, ringdown, was developed by Leda Gao, who's a student of Greg Cook and them at Wake Forest. So we are kind of two different teams, but we work together and we compared our codes to make sure that along the way, in every single way possible, we get the same results. And everything is down to machine precision, essentially. So we feel comfortable saying they're the same. They'll give you the same results. It depends what language you want to use. And then, okay, so then the numerical recipe as to how we do this. So since I'm in Portugal, I figured I'd try to add some flavor, literally some flavor to this. So the first ingredient, as you mentioned, is the quasinormal mode frequencies. So we can get them by solving Portugal's equation. And so we use a package called QNM, which is by Leo Stein, who was my advisor. That's why then the qnmfits seems like a natural way to use the other package. And so for the radial sector, we use the Levers method, which is the one that people typically use. But then for the angular sector, we use the spectral eigenvalue method that Cook and Seletsky developed. So if you want more details, it's quite nice actually the way they calculate everything. So we just coded it up. And so this allows us to just fit given any in our waveform. So that's the olive oil. That's our first thing. Then the second ingredient are many little things. So in this case, there are the cycles. So in this equation itself, there are things that are always ignored that I mentioned. So the fact that there are two solutions to a quasinormal mode frequency, the plus and the minus, prograde and retrograde. The spherical spheroidal mixing coefficients, these a lot of the time there are one plus a correction, and people just usually make it equals to 1. But in this case, we're actually accounting for the fact that, for example, the 2, 2, 3, 2, and 4, 2, so modes with equal m, have some mixing going on between them. And we also account the fact that we have overtones. Apart from that, you do multiple modes, and then you fix your frame, which is something I will explain next. And you end up with this, kind of, you fill out your equation. So the third ingredient is sardines, or BMS transformation. So this is something that I'm not an expert in, but we used it for this work, so I only know a little bit. But essentially, for numerical simulations that use this extrapolation method, and for other waveforms like RIT, Maya, what typically happens is that the final black hole has this kick. So whenever you can imagine when you binary black holes merge, there's some preferred direction of the gravitational radiation. So for conservation of angular momentum, the whole remnant system has this kick velocity. How small or not it maybe depends on the initial setup. And so the problem is that then Tucholsky's equations are written assuming that your final black hole is in a rest frame. In this case, we call it the super rest frame because we're looking things at future null infinity. So in this case, you have a much richer group structure. And in this case, it's called the BMS, the Bundy-Metzner-Sachs group. And it's an infinite dimensional group that has the super translations as a subgroup. And so what this makes it happen is that if you're taking your extrapolated waveforms that are kicked and you're trying to fit your amplitudes with Tucholsky's equations, you're already in a different frame. So you're not going to be able to do it as accurately as you wish. For example, for the 2-2 mode, maybe the difference is not so obvious, but when you look at the 2-0 mode, which has the most, let's say, kick for now, or the most memory, that's going to be more noticeable, and overall, this is going to accumulate. And the problem with this super translation is that they're angle-dependent time translations. So you cannot just say, I add a constant shift to my waveform. And in the next slide, I will show you what I mean by that shift. But the fact that if you are an observer and you're at this sphere, depending on which location you're at, your time translation is going to be different. And so in your strain, what happens is that not only do you have a shift, but you also have some mode mixing that comes into effect. And this mode mixing is different from the spherical spheroidal. So this does not come from changing your functions, but this comes from the fact that you are now shifting your frame of reference.
And what modes to mix usually?
The
strongest effect.
For the mode mixing,
You said it's in the m equals 0.
the m equals 0 tend to have the most memory, and they tend to be the most affected.
And so to which modes does it mix the 2, 0, 0?
I actually don't know. I haven't looked at the modes. I haven't looked at this mode mixing effect specifically.
Okay.
Yeah.
So do you know what time?
Yeah, I think there is an equation. There is an equation at the. I mean, I can send it to you. There's an equation that shows essentially how this modes mix, but I haven't looked at each individually.
Okay.
Yeah. And so now pictorially what we have is we have our extrapolated waveform. So this is like GW150914. And you're used to seeing it like this, where the in spiral looks like it's going to go to 0 and your ring down goes to 0. But because we have this memory effect, this is no longer true. And you instead have a waveform that is shifted. That's what I mean by the shifted upwards. So essentially, this is, if you solve your equations using this Cauchy characteristic extraction method, the signal on the right is what you get. And so it's deeply connected to the memory effect. The fact that when you have a gravitational wave passing, the memory effect causes that everything's going to be shifted up from the initial location. And so what we want to do is, well, you notice, we all know that after black holes merge and we have ring down, our frequencies should decay to 0, but here it's not decaying to 0. So what we do is we shift, but also mode mix, our full waveform back so that our ring down goes to 0. And of course, then the in spiral has to go to some negative value. But we don't care about in spiral because now it's in a different frame. So the frame of reference where in spiral is going to be different than the frame of ring down. But because we only care about ring down and we want to make sure that we're in the frame where the equations describe this, we just shift everything. So what does that mean for the quasinormal mode analysis? So this is an example of the 2-0. So because this is the most drastic, this is why I chose this one. So in blue on the top, you have the numerical relativity waveform of just the 2-0 mode for the GW150914 like proxy. And then we, on the orange dotted dash line, we have our model, but with n equals 7 over 2. And we essentially try to model this 2-0 mode. And as you notice, it tries at the beginning and then it just fails because we know that the equations have to go to 0. This is not really surprising that it fails, and at the bottom you have the residual, so the absolute difference between them. If instead you move the numerical relativity waveform to the super res frame, it looks more like this. So it's it goes to 0 now, and then our model is able to accurately fit for this. And then, of course, not surprisingly, your residuals also get lower because now your waveforms are more simple. Now, the thing I meant by you can change it by a constant because it looks like the waveform is just shifted. If you just shift your waveform, we'll end up with residuals that look like the red line. So it's not too bad. But you can bring it down about half an order of magnitude maybe or so if you also take into account the load mixing. Okay, so then the instructions of how to put this together. So to build a waveform model, I mentioned that you can pick your modes by hand, but you can also do it in a different way. I mean, there are other ways you can do it, but it's hard to also justify what's the best way to pick these modes. So what we do is we take a numerical relativity waveform that is decomposed into LM harmonic modes, and then we rank each of these modes by which one is the loudest for a specific system. So usually the 2-2 mode is the loudest, and then you go on maybe 2-1, 3-2, and so on. Once you have this ranking, you pick the loudest mode and you pick the lowest overtone, because the lowest overtone, so n equals 0, is always going to be usually, well, depends on what time, but it's usually going to be the loudest. And then as you go into higher and higher overtones, the amplitudes are gonna they're gonna have short or quick damping times, and so therefore they're going to become less important. So we take, let's say, the 2-2-0, that's the loudest, and we take into account both the prograde and retrograde modes, because depending on the system you're looking at, maybe the retrograde is more important than the prograde. So we don't want to ignore any of those. Then we say, okay, now we take our numerical relativity waveform and we take one that we just built with the 2-2-0 plus minus modes, and we look at the difference and compute the power. Once we do that, we say, okay, how much power did we actually model when just taking this one mode into account? Let's say we did 44% power. Well, that's not enough because you're not really capturing a lot of physics. So we go back to the drawing board and then we pick the next loudest mode. And the way you can do this with the qnmfits package is you can tell it what like fractional percentage you want. So I want to capture, let's say, like 99% of the power, so 0.99, and it will find modes until it reaches that number. But you can also tell it how many you want, like 10 loudest, and it will give you the 10 loudest. And you can choose to turn retrograde modes on and off. You can pick how many overtones you want. So maybe cap it at 2 overtones and then cut it there. And essentially it does this iteratively until it reaches what you want, and then it calculates the mismatch and it gives you all the amplitudes. Yeah.
Does it do it for changing static time?
Right. So this is done picking one specific time, but you can do it over a window of time. So the way we've done it, and I will show more, is we essentially do studies where we look at before the peak, all the way like -10 before the peak, 10M, and then after the peak, and just to look at how the mode content changes and the power and which modes become important and all that. So this is the machinery behind picking the modes. And so the final dish, and I included a picture of my dinner last night. So this is why the sardines, this was all planned. I didn't know what to make the potatoes, so. So then now you get to see the importance of fitting for multiple modes in the super res frame. And so this is a plot that maybe some of you have seen, where you have a different number of modes that you choose. So for example, if you start in the blue solid line, if you choose the 5 most important modes versus choosing the 20 most important modes, you will look at the mismatch between numerical relativity and your waveform model built from these modes. And over time, you calculate it at each time step and try to figure out, well, you kind of see which one is the lowest. Of course, we don't want to look at things that are, like in this regime, because at that point it's too late into the ringdown. And if we want to ever go back to observation, well, we're not going to get a lot of signal to noise if we start ringing. Here at the bottom, I've shown the numerical relativity error. So what we do is we take the highest resolution and the second highest resolution waveforms and do the mismatch. And so this is the curve we get. So we know that if we fit anything that is below this curve, it's essentially, down to zero. So we cannot really trust that. And so of course, the more modes you add up to 100, you can get very low mismatches. In contrast, we have also the purple dot dash line and the yellow one, which shows if you just take into account the 220 and the 2 minus 20 modes, that's the purple one. You can see how, you can only pick things in mismatch so much. So you cannot really do as a precise as model as you may want to. Additionally, we decided to also look at parameter estimation because something that looks like your waveform may not still be, enough to say, oh, we can model it perfectly. So here's where we do estimate the mass, the final mass and final spin. And so we calculated the error using the equation above. So we look at the change or the difference in the masses and then just the difference in the spins. And if you just take your 220 fundamental mode, you get errors that are pretty high as you add more and more overtones. So this is the median, I should say, the horizontal. As you add more and more overtones, you get lower errors. And if you just pick, the 40 most important modes, you get down to, I don't know, 8 to -4. But we stopped here because we noticed that if you start adding more and more modes, at least for, a few of the simulations, you don't really get lower errors. There seems to be a cap. So you can add 100 and then you end up here. So that's just to show that you're able to reproduce low errors. And just to show a quick demonstration before moving on to the next topic, we have here two different waveforms that we looked at. One is the same one, GW5914, which is also denoted as 0305 in the solid lines. And in the dash one, it's this CCE13 waveform, which is a presetting waveform. And I believe it's Q equals 4. So it's one black hole is 4 times more massive than the other. So it's essentially a highly asymmetric system. And we looked at 3 sets of modes and tried to just show what the code can do. We also did this initially to compare the Mathematica and the Python. This was, for example, one of the tests, and all the lines were on top of each other with 10 to -9 or something different. So we just plotted the ones for Python. And you can see how, so the first set, which is the purple, you just look at m equals 2 modes. So 2, 2, 3, 2, 4, 2. So we kind of look at this kind of mode mixing effects. If you then look at different overtones, so the second set is the yellow, you just add a bunch of overtones, you notice that your mismatches are around 0, around 6. So if you've been following the literature, there was a paper in 2019, I believe, that shows how the more overtones you add, the closer you can model your waveform to the peak of the waveform. So 0 will be the peak of a waveform. And if instead you just pick the top 20 modes, you get something like the blue line, something like this. So this is just kind of to show the capabilities. You can also look at the amplitude ratios. So all the amplitudes compared to the 220 amplitude, and you can also look at the ratios for different number of overtones, 1, 2, 3, 4, and just see how they behave.
I mean, I can say the problem of that paper is that the amplitudes are not constant over time.
Matson, or which paper?
The one on 2019.
Yeah.
I mean, you can fit whatever you want, but then the physical interpretation is not correct anymore.
Yeah, so that's another thing that I actually will talk about.
Okay.
I think maybe the next slide.
I wanted to ask, like, how do you make sure that you fit quasi-normal mode and you don't fit something else?
Yeah, exactly. And also, even if you pick, let's say, let's look at this mode, right? You say, well, the mismatch is lower around 0 onwards, so I can just take my fits up 0 and just call it, or I don't know what the expression is. Call it a day. But yeah, that's not the full story, and I will show exactly all these plots showing the stability. But okay, what if you don't have a waveform because you don't work with waveforms, but you have initial masses and spins? Then I will go into the next product, which is NR surrogate 3D Q8 RD. So these names are very unfortunate. But the reason why it's called that, it's because there's already a waveform, a family of waveform surrogates called NR, for example, hybrid surrogate 3DQ8, 7DQ4, all these numbers that whether or not you want to, you end up memorizing if you keep reading them. So essentially what this is telling you is, well, this is a surrogate model based on numerical relativity specifically, where it's a three-dimensional prediction. So you have, you know, you look at your mass ratio and some combinations of your spins, 2 of those. And then Q8 means that you look at systems that are up to Q equals 8, mass ratio equals 8. And then RD, just to make sure, you know, it's just ringdown. So we don't do in-spiral immersion, but you can stitch it to an in-spiral immersion. Okay, so this surrogate model essentially allows you to be able to predict what the amplitudes are and the remnant parameters for an area of parameter space where you do not have any NR simulations. So I think here we have tons of NR experts, so we know it takes a long time to make a single simulation, especially if you want it in a parameter space where things are very, you know, very negative, like maybe very negative or positive, highly spinning systems like 0.99x continuum. So here we built this surrogate model by using qnmfits, where we use the qnmfits package to figure out what the amplitudes and the final mass and spin are. And so we use 102 waveforms, which I know is very little, but that's all we had at the time. And it's also the same as another model, another surrogate model. So we are using the same quantity as there. But these are CC waveforms. That's the only difference. It's the same exact as, for example, VJ's 3DQ8 surrogate, but just CC waveforms. And this is the parameter space we cover. So here I put log of Q, but really it's Q equals 1 to Q equals 8. You have the secondary spin in the polar axis and the primary spin. These are all spinel lines, so that's why I have to see components only. And on these yellow dots, this is an area of parameter space where the retrograde modes are more important than the prograde modes. So this was one of the motivations why we can't pick retrograde modes, but there are different issues associated with that, which I'll get to. But you know, if you want to model black holes in that parameter space, you can't ignore it in your modeling. So what we essentially do is we take a combination of our log of the mass ratio, chi hat and chi a. So chi hat is a combination of the initial spins with the mass ratio, with the asymmetric mass ratio, and then we have the asymmetric spin here, which is the difference between the primary and secondary spin components. And the reason why we do that is because this was actually the best, I guess, the smoothest parametrization we could use for machine learning. This was also what VJ and the other surrogate groups did. But even though they did that, we still tried different combinations beforehand just to make sure that also worked best for us, and it did. So we used Gaussian process regression, which is essentially a way to predict your amplitudes using interpolation. And I can talk more about that if you have questions later. And essentially, we make a map from our initial values or initial parameters to our final ones, the finals being the mass, spin, and the amplitudes. And we actually separated the amplitudes because they're complex, we separated it into the real and imaginary components. Because there was no way for the GPR to actually predict a complex value. Not at least with scikit-learn. I think with other, I think with PyTorch and other things, it can be done. But you will have to do a lot of developing for that. And so the question is, when we were building this, is like, okay, so how many modes do we fit? So this is getting to your question. Which modes do we pick? At what time do we fit them? And so the answer for us was mode stability. So then you need to check for all these things. So the way we began doing all of this is we took all 102 simulations. We aligned them, aligned the waveforms in time and phase so that everything can be compared one-to-one. We went, I don't want to say a bit crazy, but we decided to fit 468 quasinormal modes, which is the most we could do. And then we looked at them from -10m before peak to 50m after peak, just to get an idea first of how things behave. then, because we had very different systems, as you saw, the parameter space was quite wide. We said, okay, well, now that we have this list of power ranking for each single simulation for each single time, because we also pick different times, we say, okay, let's just pick the top, the top X loudest modes, and then get rid of the rest and redo our fitting. Turns out that the mode ranking does not change, so that's also good to know that our algorithm is not sensitive to how many modes you want to pick initially for fitting. And so we said, okay, we picked the 26 loudest, which is still a bit overkill, but that's fine. And then we went from -10 M before peak to 100 M, so we just modeled at all times. And so at that point, we said, okay, from all these 26 modes, we need to make sure that they're stable. And initially, we started with less modes. I think I started with 10, but they were not all stable, so that's why we ended up going to 26. Do you have a question? To 26. So then we said, okay, with all these 26 modes, we looked at this kind of information. So we looked at the amplitudes. We started by looking at this, and we said, okay, I mean, they look flat at some point, like after 20, but that's not really a great way to quantify things. So then we took the variance over the mean absolute amplitude for each single mode, and then you get plots that look like this. And so you say, okay, depending on how much error you want to introduce. So of course, the lowest here is the most stable, and as you get closer to peak, things become more and more unstable. Well, one of the first things we notice is you see that these are separate modes, right? So the reason why this happens is because we're looking at the prograde. And so these simulations here, so each of these is a simulation, are those where the retrograde mode matters the most. So they are actually separate. They have higher variance than the rest. So we said, okay, well, it looks like things flatten out around 10. We could have easily picked something, 20. We could have easily picked something around 10, but we were like, well, why pick something with no error when we could just pick something with less error? So we went with this. And so we did this for every single mode of those 26. And you get sometimes things that look very bad, sort of like this. So the top plot is again the same plot, ignore the light color lines in the background. But then if you look at the retrograde mode, this is what your variance looks like. The retrograde is on the simulations that are very well behaved for the retrograde modes, highly negative spinning, high mass ratio, and these are the rest. So for the rest of the simulations, the retrograde mode is quite slow. It varies a lot, and you can't really do much with that, unfortunately. So then, we had some modes that were, even without the main retrograde, looked nasty like that. So we decided to just get rid of those ones, just to not add more error to our model. Another interesting thing that I hope you can see clearly is there are some gray lines in the background. Technically also here, like for example, these ones. And so those gray lines correspond to doing this fitting without the first overtone. So if you take a list of, 26 amplitudes, mode amplitudes, you do not have any overtones at all, you get the gray lines. But if you add even just a 2-to-1 overtone to your system, it corrects and everything gets closer to this time being 20. It's not that close. So it shows how the addition of an extra one overtone makes the fits better. And this is something that has also been noticed in a couple of other works, I think. We don't know why, but that's something we've been noticing. And so in the end, we said, okay, let's build a model at t equals 20, so 20 m after p, because that's when everything is the most stable. And in that case, unfortunately, we are left with, well, fortunately or unfortunately, depending on what modes you put up, we are left with this set of modes. One thing you will not notice here is that we do not have retrograde modes, because even though we can capture them very well in places like this, we cannot do this very well. And with machine learning, this ruins the data for the retrograde. So we thought about a way that we can do this where we kind of weight the data. With other machine learning algorithms like neural networks, you can physically add a loss or like a weight function. But with GPR, you cannot do that. So you can just make everything else 0 and maybe try it that way. You can also pretend that those are the prograde just for the sake of fitting, but in the end result, make sure it's labeled as retrograde, which I think another group did that. But this was a while back, so we just left it that way. And we do have those at 2,2 and 2-2, so we do have those modes. We have the first overtone that we kept because it was stable and we think it's nicer. We have the 2-0 mode, which is important for the memory, and then the 3-2 and 4 modes. And so maybe you'll notice that there are no odd M modes, and that's because they have this high rotation. And at the time, nobody knew why they were not like, well, the 2-1 was not stable, first of all. So that one was thrown out. And things like the 3-3, or even 3-1, there was this rotation that at the time nobody knew why we couldn't model it well enough. So we didn't want to add any junk to the model, so we just completely ignored it. Yeah.
So nowadays you know.
Sorry?
Nowadays you know how to model.
Yeah, now we know how, but then I started a new job and I haven't had time to go back, but it's on my to-do list. Yeah, we can essentially, like, I think we can just rotate the whole waveform by pi, and then from that way extract the m=1 modes or m=even modes. And we think that's what works, and it seems from Constantino's paper, they also did that. But we haven't tried it again.
Okay, so maybe we take that for future.
Yeah, it's on the future work list. Okay, so then another thing that you may have wondered is, well, I mentioned we only have 102 waveforms, and although that seems good enough for waveform surrogates, if you do machine learning or read about big data science and stuff, you know that that's not a lot of data to go off of. So how do we calculate the errors if we can't really do test with a different data set? So we do this k-fold cross-validation, and essentially you divide. This is perfect for small data sets, so you don't bias your results, because you end up testing over your full data without getting rid of a chunk of it, essentially, which, already 102, you don't want to get rid of 20 waveforms. So the way we do this is we divide, if you look at the top line just visually, you divide your data into mostly training and testing, and then we divide this into different number of folds. So each fold has a certain number of waveforms. I think for our case, we ended up with 6 waveforms in each fold. And so if you divide your waveforms into 6 sets, you test over this. Sorry, you train over folds 2, 3, and 4, and then you test over the first one, and then you get some error. And then, of course, if you do that once, that's not good, because what if your testing set has something that's like very negative for spinning, but everything else here is, not spinning, for example. Then you do the same thing. So now you take the second fold as your testing, and then you train over everything else, and you repeat this until you run out of folds. And then each one of these gives you a different error. And then because of that, you take the mean value of these errors, and you get an idea of what your full model error is. So that's how we've been doing it. And so just to give you then some numbers. So here we have listed the median relative errors for our quasinormal. The results are essentially the same for the minus m minus program modes. So I didn't list them twice because they are, I think they vary at like 10 to the -6 or something. So we don't really care about errors at that numbers. So essentially here we have the real part error and the imaginary part. And the way we did this was through the relative difference or relative fraction method. So we took the amplitude from a quasinormal mode model and from the surrogate, and then we divided it from our original model and saw the error. So you notice across it's 10 to the -2, 10 to the -3, depending on which mode you look at. And if you just take the absolute value of the whole mode, you get this third fold. So it seems to be doing better for full mode, the absolute value, better than each component individually. And so here's an example of the plot. Well, this is a little bit different than the previous plot, but it shows also parameter space where you have the mass ratio here, and then you have the effective spin on this axis and the error color coded. And so you will notice that, for example, some of the higher errors are in this area where the retrograde mode is, because here we're just plotting the two further. And so we have plots essentially for each of these modes. So you can kind of get an idea of if there's an area of parameter space where you're not modeling as well, and then what you can do about it to take care of that portion. So the whole point of this was not just to be able to get the amplitudes, but then to make a reconstruct the model back. So although the hybrid or the NR surrogate 3D Q8 model really only gives you amplitudes and spins and masses, it also provides you with the function where you can put that back in, and it pops out a waveform. So here we just chose the 2-2 mode, just as an example. And this is the worst case scenario that we have over all of these waveforms. So we took FXS 1450, which has all these parameters, and we plotted it in black. Then with the quasinormal mode model, we do, or qnmfits, we fit these amplitudes or this amplitude and build our model, and that's the blue, which, I mean, everything's on top of each other. But then you do this with the ringdown surrogate, you predict them instead of fitting them, and then you get the orange dashed lines. And in the end, the difference between numerical relativity and the ringdown surrogate looks like this. So that's the, sorry, I thought worst case scenario. This is the best case scenario. The lowest mismatch, because this is 10 to the negative 3 or so. Of course, this is for the 2-2 mode, right? Specifically. And depending on which mode you're looking at, the worst, I mean, it's going to change. And then you can also say, well, I just want to include a bunch of modes. So here we just pick like a theta and pi, so pi over 3, pi over 4. So you can think of a location on the sky and look at the modes at that point, and you can reconstruct the waveform and still get errors of, or mismatches of, you know, a little bit under 10 to the negative 2. So this is just to show that you can get some waveforms. Overall, we did a study with a bunch of different waveforms, so then we can get an idea of what the median will be. And so for here I have the medians in these circles. So for example, you have, here is a numerical relativity mismatch where you again take the highest resolution waveform and the lowest. So this is the lowest we can ever expect to get. Actually, we don't want it to be exactly that. Probably we want it in here. Then we also compare numerical relativity with the surrogate model. So that's with blue. So it's still, I mean, it's still 10 to the negative 1 10 to the negative 2. Then you have the quasinormal mode model, so qnmfits versus the surrogate, which is here. So we just, since it's built on it upon the surrogate, we're not surprised that, you know, this is much lower. And then you have your numerical relativity and the qnmfits package. So we did all of this just for, just because we didn't want to not compare any possibility. So you can see the mismatches are actually quite low. I don't know, well, if you're all familiar with mismatches for surrogate models, but these are these are on par with the models that people currently use that are some of the best ones. So it's good that we didn't get worse results. We also did again parameter estimation, trying to see how the errors of the final math and spin are. And so we also see that they are, you know, 10, I mean, they are 10 to the, I don't know, 5 times 10 to the negative 5 or something like that, approximate the median. So also on par with hybrid surrogate 3D Q8. So everything's looking good. And yeah, so that is that. And I'm almost done, I promise. Are there any questions about this surrogate model? Okay, so I'm pretty much at the end here, but one thing I wanted to talk about is length and ringdown. So now I'm moving a little bit into doing lensing studies. And the one related to ring down is still very much starting. So I don't really have proper results or a good analysis, or I haven't found anything groundbreaking. But essentially we're trying to say, okay, if LIGO detects a binary black hole system that is mainly ring down, which there have been some events that we already know about, how are we able to look at that ring down signal and say, we know it has been lensed because, you know, there's this signature from ring down that we can see clearly. So what I'm looking at is how the quasinormal mode amplitudes that are lensed are affected. And this could be ideal for being able to more accurately detect, because so far we have not been able to say, oh, these waveforms have been lensed. So we have detected zero lens waveforms and like that. And of course, we know that, you know, I don't know how obvious it's going to be, but for example, with LISA, we're going to be able to detect, I mean, these gravitational waves are going through clusters of galaxies and stars, so of course they're going to be lensed. So it'd be interesting to kind of get an idea of what signatures we can find. Maybe the mass ratios will change, or maybe there will be like some deviation. And so in that case, this is also kind of related to test of GR, because we want to be able to say, okay, if this is how things change, then how does that put a constraint on test of GR, like beyond GR theories, right, of how much things can vary, the amplitudes. So this is something I've looked at. So just to show you, so this is kind of small, but I wasn't sure how to make it bigger without blowing it up. So essentially we have a numerical relativity waveform, which is, so it's here in blue. And we have the quasinormal mode model, which is qnmfits, right on top of it. And then you see there's like a sheet, and that's the lens model with the qnmfits. So something interesting that we found so far is the following. If you look at the residuals between all of these waveforms, so between numerical relativity and the qnmfits model, you have this blue line. So, okay, yeah, it looks good, it's quite low. If you then look at the difference between lensing, the lensed waveform and the lens QNM model, that's the green, but that's already starting to be high. So that's something that we don't know why. So, you know, first of all, it's always a little bit higher here, except for this peak. But then you notice that around 50 m onwards, it seems that the lens model is not as close as the unlensed model. So there's already something there that we're not sure where it comes from. And then another thing is the amplitude. So these are the complex amplitudes at every fitted at different times and for different modes. So for most of the modes, like the 2-2, they're both on top of each other. So the dashed are the lens and the solid are the unlensed. And so here you can't see the lens because it's on top of the lens. But here they start to deviate. But this doesn't worry me because we're like past 100 and I don't care about any section. If you're looking for tails, sure, but I'm not. So you know, weird. I'm wondering why, but okay. But then, for example, for the 2-0 mode, you have this that it's never everything is on top of each other for other modes, but not for the 2-0 mode. There's some difference, but it very quickly around maybe 30 m or so, it just kind of deviates and doesn't go down to 0 as much as it should. So this is a big question mark right now. And so we're finishing working on the actual math to see what to expect from these lensed waveforms.
So the dashed ones are the lensed ones.
Dashed are lensed, yeah. The solid are unlensed, so just enough.
So then you said in LIGO you have seen some signals where you only see the radar.
In LIGO, we have seen only on lens. Oh, sorry, yeah, only on lens signals as far as we know.
Yeah.
And there are a couple that I think are public. I actually haven't kept up with the not public ones, so I actually can't tell you. But there are a couple where it's very heavily, mostly just ring down with very little in spiral. And there are some papers about, I think by Juan Calderon Bustillo, for example, was one of the first papers I remember coming out. Was it like 05 something 21?
So, but what these sources would be very heavy black holes?
Yeah, they're very heavy black holes. And so it's mostly ring down. So a lot of the waveform models that are very good at in spiral and less accurate in ring down you can only do so much with them. So it'd be nice to be able to do some study with this, more accurate ring down and see what we can find. So ideally we connect these to observation, but there's, apart from one obvious way to do it, creating a template bank and doing match filtering, we're not really sure how else we can make it, come back to observation. But of course, any findings we make are interesting. And then, yeah, just for future work. So one of the things you mentioned, so we want to include quadratic modes in the qnmfits package, so that's on the way. And then once we do that, it'd be much easier to then just do add quadratic modes to the surrogate model, as well as the retrograde modes and even M modes. Ideally, you'd build a processing surrogate. So there is one that came out last week, I believe, but it's not, well, obviously nothing is perfect, but there's still some work to do because they don't do spherical spheroidal mixing. They don't do retrograde modes and they don't do overtones. And I think it's only about 4 modes or something. So there are still a lot of ingredients missing, but there is a model that has some processing waveforms in there. So hopefully, I think soon there are people who are working on doing a processing model. I was going to work on it, but other people in SXS are working, so I'll just let them finish it. And then we are also working with ring down waveforms in the lens regime and trying to see what we find. So that's my future work. And then I'm just going to leave this to here with you in case you're interested in at least taking a look at it. If it's useful, good. If not, well, it exists. So thank you.
Any questions?
So the Anaxur model is available also on that link.
Yeah, so Vijay Varma has this surfing black hole package, and within that package there are now 5 surrogates. So it's within that link, and they're listed on the README 5. So mine's the 4th.
Okay.
Yeah. I mean, there were lots of questions to ask.
Yeah, saying that for the lens, can you say a bit more what exactly the waveforms to get the lens? Yeah.
So well, first of all, we have all the waveforms in the time domain, right? Well, what I'm using as PC waveform. So the problem is that if you want to lens them, all the equations for lensing are in the frequency domain. So I'm doing a Fourier transform on the waveform, specifically on the ring down part. So if you do a Fourier transform in the full waveform, there's some spectral leakage. So you don't, for our purposes, you don't want to do that. So we're cutting off the waveform at some point, not at peak because we care about peak, but a little bit earlier. And then we're trying to do some Fourier transform. Then we multiply that h of f waveform times our magnification amplitude. So the magnification depends on what source, on the mass, well, technically on the mass of the source that's doing the lensing. And it depends on things like distance, but because we're not doing that right now, we're multiplying it essentially times some amplitude that could be amplifying it or demagnifying it, and then some phase factor. That's essentially what it's doing. And then once we have that multiplied, we take an inverse Fourier transform, and then we can do a ring down analysis. It'd be nice if our waveforms are already in the frequency domain, because then we wouldn't have to do this, or if the lensing equations could be used in the time domain. But everything for lensing, as far as I've learned, it's in the frequency domain. So you have to do this back and forth. Yeah, but
so this when you showed this line with this comparison, you have this tail sort of that was really high.
yeah.
Are you sure that this is due to lensing, or is it maybe due to spectral leakage and cutting?
I think it's used to doing the Fourier transform. I think it's because of that. I don't think it's the lensing, because the lensing, it boils down to having some amplitude change and some phase shift. And so one of the things we're looking at is it phase shifts the whole waveform, but how does it phase shift each individual frequency? So that's what we're taking into account. and seeing if we can find something interesting there.
But you said before doing the Fourier transform, you truncate at some point the
Yeah.
waveform. Why do you do that?
Because
Can't
if
you do the truncation after transforming back?
n-
I mean, you have the full
yeah, so
waveform from
I
spiral
first have
method
the
to
full
ringdown.
thing, right? And then I truncate it and apply windowing, so it goes to 0 on both sides, and then I can do the Fourier transform, do some multiplication, and then invert it back. Because I talked to Gregorio and he says if you don't cut off the waveform, you get some, I think it's high frequencies coming into your ring down, higher frequencies. I don't remember anymore because this was a long time ago. But you get some spectral leakage of frequencies that you do not want, and it contaminates your ring down. So you have to cut it.
Yes, yes, yes.
This was something, yeah, this was something we did. And initially I was doing the full waveform. And then only at the end doing the ring down analysis after cutting things up, but talking to him, he said the right way to do it is to cut ring down. It's on his thesis, if you want. I was trying to read it to understand it as well. So I don't know if for in spiral, if you only care about in spiral, maybe you also have to get rid of the ring down and the merger and just put that.
Because I'm thinking like, I don't know if there is lensing, maybe.
Oh, cumulative effect?
Yeah, exactly. Like also in spiral might enter in the
Yeah.
lensed waveform at the ring
Oh,
down.
right, so the lensing is frequency dependent. So as long as you have your ring down frequencies without any spectral leakage, I think your lensing will depend on each of those frequencies. I don't think it will affect it, as
Okay.
far as we understand. Yeah, it's not super clear.
I don't know. I don't know.
Yeah, I mean, I think there's always some sort of error, right, that you can't get rid of, from what I understand. But you want to make sure you only have the ring down, and then the lensing on top of that should not add anything. But I'm also very new to lensing, so I don't know a lot the details.
Maybe, of course, I have a question on the quadratic modes.
Mhm.
Because so you say you want to include them, so you want to fit also for the amplitude, I
Yeah.
guess, because you know that you can compute them.
Yeah,
So
yeah.
it would be interesting to
It's-
compare then what you fit to the prediction.
Right,
You can
yeah.
get.
And this should be, I mean, this is very easy to implement for us because it's the hard part is already done.
Mhm.
I just haven't prioritized it. But I know you also have your fits, or not your fits, your,
Yeah, it's
don't know what-
computed in the
you
same way that
computed- yeah.
the frequency.
so one could technically add your quadratic modes
Mhm.
into the surrogate model.
Yeah.
Without even, or you don't even need to add it to the surrogate model. You can just get them from your fits. And then when you put the model together.
Yeah, or you could fit it like the other and see that it's consistent with the.
Yeah.
the-
Yeah, yeah.
If you enjoyed the video, like and subscribe.